Hello, my humans.
Hello, students. I don't know which of us is being more inclusive. Either we have students that are not humans and then I am, or you're including all humans that exist and then you are.
That's right. All of humanity is
I
welcome
like
to
it.
watch this video.
So we're doing some proving stuff today. That's exciting.
Proofs scare me. I don't like them. I'm scared.
Well, that's okay because our students don't know yet to be scared of them, so they're going to enjoy them because they're fun.
Oh, that's right. I actually like proofs.
All right, so we're going to start up by solving for a variable, and we're given the information that ray BD bisects angle ABC. As soon as I see that, I'm going to draw something on this picture because I know that bisecting, because of the Greek, means two pieces and cutting it. So that means that our two angles are going to be labeled as equal because those are two equal pieces based on what Mr. Butterworth is writing now.
I like how each time bisect has come up when you've been talking, and so you've gone to the Greek each time. I'm sure the children are like, "What is he doing?"
I know, it's
But,
great.
I think it's important to note also, just kind of following up on our geometry stuff. We have BD. That's a ray. And actually in the picture, it's not a ray, so let's make it a ray. I like how we both made the
I
arrow.
do too.
And I would have put like D here, so we'll pretend that D is not there. So now we have ray BD bisects angle ABC, and you made the little archy things which show that those two pieces are the same.
Yeah, one of the things that I always try to do as soon as I read a problem is to draw on the diagram the things that I can get from that problem. I think that's a really helpful way to try to figure things out that I may or may not know what's going on. So I think now that we've talked about what this means geometrically, now we can set up some kind of an algebra thing.
We can say 3 times 2x minus 5 is going to be the same as 2x plus 10 plus 1.
And I'm thinking that because we know something about multiplying across things that are being added or subtracted, I think we call this a distribution system. I don't even know why I add system to that, so just go with it.
I was thinking property, you said
That's
system.
what I was looking for, and system is what came out. So we're going to do some distribution. And we've got 6x and a minus 15. And on the other side, I like that. This looks great. Now we have an x on both sides. I wonder if we were practicing doing some algebra for a reason, maybe like this reason. When we're trying to combine things so that we get like terms all together, one of the things I like doing is getting rid of the smaller of the x's if we have it on both sides. So if I've got 2x and 6x, I'm going to probably subtract 2x from both sides.
I'm going to combine the 20 and the 1 also. We're going to do two things at once.
I like it. This is going to be awesome. And I'm going to keep my minus 15. And 20 plus 1 is indeed 21. All right. Now to continue getting the x by itself, we know we've got to get rid of the 4 times and the minus 15. We generally like getting rid of things in opposite order of operations because it makes it less messy to deal with. And we're left with 4x, 0, and 36.
Is that SADMAP?
Yeah, I don't like formalizing that as a...
I was just trying to say the word backwards.
Yeah, some people do formalize that as a thing, like you have to do this in this order. And the truth is you don't, as long as you're doing things that are mathematically okay. We do that order because it makes it less messy because we don't end up dividing everything and get fractions. Speaking of dividing, we're going to divide both sides by 4 and get x is equal to 9.
And I appreciate that you didn't put an equal sign there. You did that arrow there.
You thought I was going to go equals, didn't I?
Equals, and then things get... I mean, actually, mathematically, those would actually all be equal. So in this case, this basically...
That is true.
Case, it would work. To double check that you are right, if you wanted to plug back in, you could plug in for the x there and the x there. And if you get the same answer, then you did it right.
Cool. I like that. All right. And this one is not telling us that we want the values of each angle, so we don't have to plug it in to get those, just to check our work. Cool. All
This
right.
page has a whole bunch of scary stuff on it. It's okay, keep reading. These are all things you know, especially these top ones. The addition
Ooh.
property says you can add equal things to each side. The subtraction one says you can subtract equal things from both sides. Same thing for multiplication and for division. Mr. Carlson basically already did all of those things in the previous page or on the previous page.
What? You mean this is stuff that we've been doing since like kindergarten?
Not quite kindergarten because my young daughters don't know all this stuff yet.
Oh, okay.
Yet.
And then we have some newer-ish properties. Some of these will be new, and some of these are ones that we talk about in other courses as well. Basically talking about things that we generally accept as true anyway. A number is equal to itself. We can set up equalities in either order. It doesn't matter if we say like x equals 3 or 3 equals x. And then my very favorite property is the transitive property, which if we have kind of a line of things being equal to each other, it lets us skip to the end and talk about kind of the beginning of that train and the end being equal. And then substitution is something that we've been using for a while as well. If we say that two things are equal, we can replace one with the other in any mathematical equation that we're working with.
I like it. There's one more property. I bet it's on the next page.
Oh, I bet it is too. I wonder if we've already used it.
We definitely have, although some people call it something different and it's weird, but most of us call it the distributive property.
Oh, you were making fun of my distributive system again. I thought you were actually talking about people having a different name for this.
I know, I could tell by the confusion on your face, but no, I was just saying that because I don't know why anyone would call it a distributive system. But anyway, this is the property we know and love. You could also just, for funsies, you could also have it this way.
It's
That
true.
might freak people out, but it doesn't matter because multiplication, once again, is commutative.
Hey, that sounds like another property.
It is. The commutative property is also the associative property, but we don't talk about those much here.
No, it's true.
And often we ask you to write formal proofs of what you're doing. This year, we're stepping back on that a little bit, but we still want you to know what you're doing. So you don't necessarily have to write up formally exactly what you are doing, but you need to know why you're doing things. So I'm going to show you kind of what we would write, or maybe Mr. Carlson will show you what we would write as I do the problem. So I will explain the problem, and then on the right, Mr. Carlson will write down kind of an explanation of what I'm doing. So my first step is I'm distributing that 3 to both the x and the 3. So that's 3x plus 9 minus 2 equals 7. So Mr. Carlson's writing down, we use the distributive property, or system.
Or
and
system.
if you want to put more details there, use the distributive property, multiplied 3 into both x and 3. You could put more details there if you wanted to, but you don't have to. So we use the distributive property. Then I'm going to go ahead and combine that 9 and that 2. You don't have to. You could start moving them to the other side. But I'm going to combine them by combining like terms.
And then again, this is one that sometimes we don't always need to say, but it's really nice to explain your steps of what you've done.
And then I'm going to subtract 7 from both sides because I want to get the 3x by itself. So on the previous, not the previous page, but the page before that, they called that the subtraction property of equality.
I'm going to write subtraction. Because I did almost write subtraction.
Subtraction, I don't know how to say that. And then I'm going to divide both sides by 3.
And I'm going to say division.
Right, so you don't have to write like subtraction property of equality. It doesn't matter that much in terms of kind of the formalization of this, especially this year, but we might want to ask some of those at some point.
So one way to think about this in a way that's not scary, because a lot of students do become afraid of proofs in geometry, is to just say why or how you're doing each step that you do. And that's true in both the algebraic versions and the geometric ones that we're going to see. Ooh, this one looks fun. Do you want to swap roles?
Yeah, buddy.
All right, I'm going to draw a line down the middle. And I'm going to start out the same way I think that you did in the previous one. which is to do some distribution. I feel like that should be a dance move. Do the distribution. I'm going to be real careful because -2 times -5 is +10. All right, I feel pretty good about that. I'm then going to do the same exact thing that you did in the previous one. I noticed that 4x minus 2x I can combine to make 2x, and 10 plus 7 I can combine to make 17. I'm going to keep the 5 on the other side and make that go like that. Cool, and that is combining like terms. Now I've got 2x plus 17. I know that if I want to get the x by itself, I'm going to take 17 away from both sides. Oh, I drew my line a little bit too soon.
No. Oh, yes, you did. I was starting to write, and you had just written it underneath me. Ooh, that was so satisfying to watch you erase that.
We got -12.
So I'm explaining it a little bit differently on the right, just as an alternative way to kind of think about it.
So you're saying not only kind of what you're doing, but also more explicitly, like what are you taking away from both sides?
Yeah, I didn't for the combined like terms one, honestly, just because I was lazy because you did two different combinings. But I'm trying to be a little bit more explicit with what I'm doing. Yes.
Sure. All right, and then for a last step, I see I've got a 2x. I'm going to divide both sides by 2.
And we're going to pretend that Mr. Carlson knows how to divide and get rid of that one.
I don't even remember writing that one, so I'm going to blame you for that. Woof. It's a fun one. So again, this is really just kind of showing why we can do the things that we're doing. But it also looks a lot like how we're doing the things that we're doing. And sometimes it's a little bit unclear, the difference between those two in math. And that's okay.
So this next one brings us to geometry. There'll obviously be algebra involved, but brings us to geometry. So I think there's a number of different ways I could start this. I think what I'm going to write is this. The measure of angle AOM plus the measure of angle MOC equals the measure of angle COA.
All right, and we had a postulate that we've used to describe this. It's called the angle addition postulate. To me, I think that's something that's pretty clear just based on the diagram in this case. If we were looking at something that was super formal, we would ask you to explain why is it okay to add these two angles together, but that's not, again, that's not this here.
Actually, I think we could do it this way. So let's go through it and then we'll kind of do a quick little paragraph.
Sure.
So, and then AOM is 2x plus 30. MOC is x, and COA, this is the part where you got to use your thinker there. That's going to be 180.
That's true. That's a pretty straightforward answer there.
That's right. So my little paragraph, if I was saying that, I would say two adjacent, see how I use the word adjacent in there, angles add to the whole angle which is 180 degrees. So that kind of gets me started on what I did there. And then if I wanted to say, you didn't like my word is, yeah, my is's come out weird. Kind of like my cosines and sines, but they don't know what that is yet.
That's fair.
So then if I combine those like terms, I get 3x And so I could continue my explanation of what I did, but I don't want to write it all down because I'm feeling lazy. And then subtract 30 from both sides. So that's 150. And then divide. So I get 50.
So would doing something like this and then say, and then I used algebraic properties to solve for x,
That's totally fine. Yep.
because
I think
that's, I mean, from my perspective in general, students have been adding, subtracting the same thing to both sides for quite a long time. These aren't new things, but now we're writing them in ways that seem new and scary, but this is nothing that's new.
right. But I think that would be fine. Obviously, we don't have that much room on this page to
Right.
do that. We're trying to write kind of big for them. But yeah, if they wanted to explain it further, they could say, I then combined like terms, and then I subtracted 30 from both sides and divided by 3 and figured out that x was 50. Sure, go for
Sure.
it. Not
And,
going to hurt you.
and on something that they'd see as like an assessment, I think that you and I are more likely to give them something that asks them to describe what they did and showed someone else's work.
Yeah, I
And
think that's good.
I think that makes sense for that. All right. So now we have a new thing that we're, did the last one have a given? Or did it say given? I don't think it did.
No, I mean, the given was just a picture.
Yeah, so we have a new word here. When you're given something, that means that this problem is being given to you with information at the start of this problem. And this is kind of similar to the one that we looked at the very, very beginning of class. And you may remember that I said, as soon as we see something like AB bisects angle RAN, again, I want to think that because of the Greek, bisect means to cut into two equal pieces. So we're cutting this into two equal pieces. That's going to let us understand what's going on. It's also a matter of the more that you can draw in your picture at the beginning, the easier it's going to be for figuring out where things go in more complicated diagrams. So you've put this into words and you've talked about each piece of this separately, and that's looking at angle RAB and angle NAB.
RAB are the initials of my dad, in case you're curious.
Oh, that's nice. Okay, and I feel like as soon as we do that, then we're kind of good to go and we can really power through this, because I know that x must be equal to 2x minus 75. And if we're looking at that, now we have an algebraic equation. We know we can minus x from both sides. And that's going to give us 0 is equal to 1x. I'm about to write 2x again, minus 75. I'm going to add 75 to the other side. And 75 is equal to x.
Love it. You could have solved that equation differently. So if your brain didn't want to move everything away from one side and get a 0 there, if you had subtracted the 2x, you would have had negative x equals negative 75. And if that's the case, then x is 75. Just in case you're thinking differently.
That is very true.
So quick recap, Mr. Carlson drew on the picture of what was going on. I then put in words what's going on, and then we just solved the equation from there. And if you can do that, honestly, you're doing great.
Cool.
This page is designed to scare you.
It's true.
But all it is the exact same properties. The only difference is instead of equal signs, we have these congruent signs. That's it. So don't fret. It's a slightly different thing. Congruence is different from equality. It has to do with transformations that we don't really know about yet. But for our purposes, right now, we're not going to get too much into that because we just don't have the time for it.
Yeah, and really these are all the same things that we've done before. But now they look a little bit fancier because we're talking about segments and angles instead of just variables. All right, we're going to kind of ignore the idea of this crazy thing called a two-column proof and just talk a little bit about what's going on here. So again, we're given some information, and the information, oh, they've already marked it on here. That's nice of them. So we're told that angle 1, its measure is equal to angle 3. Cool. And then we want to show angle AEC. Okay, I'm just going to mark this in scribbly green just to take a look at that. And we want to then show that's equal to DEB. So I'm going to start at D and do this one in blue. So we want to show that the green and the blue angles are equal to each other.
I don't know if this is a good idea. I just started writing, but I don't know if it's good. I said since 1 is 2.
Mm-hmm. 1 is not 2.
Sorry, 1 is 3. And then, thank you. And then AEC is 1 plus 2.
I like it.
And DEB, for the angle, DEB equals 2 plus 3. Then we can say measure of angle 1 plus the measure of angle 2 equals the measure of angle 2, or maybe I'll write it correctly because that'll make them feel better. 3 plus the measure of angle 2, which means measure of angle AEC is the same as the measure of angle DEB. What are your thoughts, Mr. Carlson? How'd I do?
I really like the part that kind of sticks out to me is this one, because that's how my brain interprets this, that we've got the two outside parts being equal, and both angles also include that middle piece here. So when we're taking two things and then we're adding the same third thing to each piece, we're keeping them the same. We're adding the same thing to both sides, basically. The beginning stuff is kind of you're stating the setup. You're saying that angle AEC is defined by being made up of those two angles. Angle DEB is defined as being made up of those two angles. So that way, when you're getting to this part where you're saying that we're adding these to both pieces, then that makes sense to me.
And so I guess in words at the end, if they could write a little quick explanation, I would go with, since 1 and 3 are the same, if we add 2 to both 1 and 3, that's still equal.
Mm-hmm.
And then 1 and 2 is AEC, 3 and 2 is DEB, and so the angles are equal. I think if they could articulate that, I think that would be great. If we're doing a formal proof, it's a little bit different. We'd have to, like, when I come up with the AEC is 1 and 2, you'd have to talk about the angle of distributive. We're not that concerned about that. We want you to be able to articulate kind of why this stuff's happening.
Yep, I think that makes sense to me. All right, and then one more. Hey, we had angles last time. Now we have segments. And in fact, this, to me, the setup looks very much like the one that we just did, to the point that they're like identical. So if I were to say something like, okay, so we're showing AC and BD are congruent, that's this one and this one.
And I like that you're looking at where are we going before we think of how are we getting there.
That's really important. In fact, sometimes when I'm working with students on how to build this skill, we will literally write out, okay, that means that segment AC is congruent to segment BD, and then kind of work backwards. And that's totally fine. There's nothing wrong with that. We're also given this information. They've pre-marked that on the diagram already, so I'm going to kind of begin that same way that Mr. Butterworth did. Since segment AB is congruent to segment CD, and we can talk about segment AC. I'm going to use mixed notation here, which is going to irritate me a little bit, is built from these pieces.
So the mixed notation Mr. Carlson's talking about, because I could tell that this was coming as he was talking. He said congruent stuff with the A, B, and C, D, but now he's using equality. Again, those are similar concepts, but they are different. And so mixing those two is a little bit uncomfortable for those of us that have a little bit of a more solid understanding of what that means. But it's okay. We will get there.
Yeah, and you really can't add two segments together, but you can add the lengths of two segments together. And that's, if that's making your mind disappear, forget I just said it. It's fine. And so with that, I'm going to change colors because why not? Because I did the AC part. Let's do the BD part now. So we've got segment BD. Its measure is equal to the measure of BC plus CD.
You said BD, but you wrote BC. I
Oh,
got you,
fun.
dude.
I was confused. I was like, what did I do? So that's kind of the background stuff that we get from this. And because of that, we can say something like this, that if AB plus BC is equal to, and I happen to write them in this order, BC plus CD, because again, we're starting with two things that are exactly the same, and we're adding that same middle piece to both of these.
And if it made you more comfortable to write on the right CD plus BC, so you can have the plus things in the same place, that's totally fine.
Yeah, the only reason that I chose to do that was because I had written it in that order up there,
Yep.
but it doesn't actually matter. And that also tells us, since AB plus BC is AB, and BC plus CD is BD. Did I do it again?
Except you said it wrong this time.
Oh, did I say?
You said it and wrote it as AB.
There we go.
We know you meant AC.
I did. Two things are congruent if their measures are the same, and here we're showing that their measures are the same, therefore they are congruent, which also is the thing I had written down below, and then forgot that I had written it down below.
It's fine. We did it.
We did. All right.